And in a polar covalent bond, we have electrons that are shared unevenly, right? So uneven distributions of electrons within a polar bond. So on the levels or on the scale of bonds, right, we have nonpolar covalent bonds, which means they share evenly or really close to evenly. We have polar covalent bonds, which means they share unevenly. And then we have ionic bonds. What are ionic bonds? What happens in an ionic bond? Do you remember? It does what? Good. Ionic bonds give and take electrons. So one gives it completely away. They form formal charges, right? And then they hang out really close to each other because of those formal charges. Okay, so that's kind of the scale of bonds. But today, we're going to look at polarity within an entire molecule. So not just within individual bonds between two atoms. We're going to look at it between the whole molecule. So a molecule is considered polar when we have what is called a dipole moment, which sounds much more dramatic than it is. Okay, a dipole moment means when we have electrons shared unevenly throughout the whole molecule. Okay, so I'm going to show you how a dipole moment is represented and what really that means. But a dipole moment means electrons are shared unevenly, right? That's really important throughout the whole molecule, not just between bonds, not just between individual atoms. So let's look at HCl. Right, the Lewis structure for HCl is really simple. Right, you need 8 electrons. It fulfills the octet, right? It's very simple for HCl. Within this molecule, there's only one bond. So it's pretty easy to tell if it's polar or nonpolar because there's only one bond we have to look at. But between hydrogen and chlorine, which of those is more electronegative? Chlorine, right? And if you don't know, look on your electronegativity scale, which is on the back of this sheet. Okay, chlorine is more electronegative, which means in this bond, if we have 2 electrons, right, if they each contribute an electron, they might be a little bit more closer to chlorine, right? They're going to pull them a little bit tighter to chlorine. So within this, the way we tell if a molecule is polar or not is we decide as a whole, are the electrons shared evenly or unevenly? And in this molecule, they're shared unevenly, right? Chlorine wants in more, and there's only one bond. So the way we show that, we show this dipole moment, is with an arrow. And we draw it over the whole molecule. So we draw the arrow in the direction of the most electronegative side. Okay, so we draw an arrow toward where the electrons would be going. And then we put a little positive tail on the arrow, which shows us this is the positive end and this is the negative end. You can draw it above it. It doesn't matter. I mean, you could draw you could draw it like this. That's fine. Yeah, it doesn't have to go over the top. It's not that big of a deal. Okay? But the important part is that you draw this tail on the positive end and you draw it toward where the electrons are located. So in a polar molecule, you'll see a kind of a location of where our electrons are. Either they're all on the outside or they're all on the inside or all on the top or the bottom, whatever it is. We'll see a kind of region of electrons, and that's where our arrow goes. Okay? A really big clue for when a molecule is polar is if it is asymmetrical. Okay? If a molecule is asymmetrical, that's a really good clue for us that it is a polar molecule. Another really good clue for us that the molecule is polar is if the central atom has lone pairs. Or a lone pair even, right? If there's a lone pair on the central atom, that's a really, really, really good indicator to us that the molecule is polar. Okay, like 99% of the time. Okay, so we're going to look at molecules as a whole to determine if they're polar or nonpolar. And I think it's almost more difficult to look at it when you just have 2 atoms, but we'll look at a few more examples here. Okay, let's try water. Lewis structure for water. We should be able to draw the Lewis structure for water without thinking at this point. Right, oxygen gives us 6. Each hydrogen gives us 1, so we should have 8 electrons, which we do. So to determine if our molecule is polar, we look at the individual bonds, and we say between this hydrogen and this oxygen, which is more electronegative? Oxygen. So I'm going to draw my little mini arrow towards oxygen. And it would be the same for the other pair, right? The other bond. Okay, these are kind of like mini little dipole moments. These show us like the small polarity arrows. Within the bond, the electrons are pulled toward oxygen. Okay, so as a whole, where are the electrons located in this molecule? Toward the top or toward the bottom? Toward the top. So my dipole moment for this molecule looks like that. It's kind of a combination of those two arrows. Right? This is called my dipole moment. Man, I can't write today. So it shows us where our electrons are located. You'll notice it also points us toward those lone pairs. Okay? If we would have drawn water with an incorrect Lewis structure or incorrect shape, right? A lot of us like to draw water like this. It doesn't really show us where our electrons are located, right? It's kind of hard to draw our dipole moment here. So when at all possible, if you can draw it near the three-dimensional shape, it's going to give you a better idea as to where our dipole moment is really pointing. Does that kind of make sense? You don't have to get fancy with tetrahedral and things like that. But for ones that have lone pairs, you really just need to be thinking about, okay, three-dimensionally, where are those lone pairs going to be located? And that's where my dipole moment needs to go. Okay, more often than not, that dipole moment needs to go toward the lone pairs. So here, that doesn't really work, right? I can't draw my dipole moment anywhere. Okay? Okay, CH3F, carbon should have been our central atom. Okay, so where do we think polar or nonpolar? Polar, good. It is polar. And where does our dipole moment need to go? Toward fluorine. Yeah, exactly. So not specifically down, but toward fluorine. So on this chart, yes, down. In yours, wherever you drew fluorine, that's where your dipole moment needs to go. Because between carbon and hydrogen, right, it goes here, and here, and here, right? And then between carbon and fluorine, it goes toward fluorine. So our dipole moment needs to go toward fluorine, wherever that happens to be.
Wait, so on this one we have to draw all these arrows?
No, you don't have to.
Oh, okay, those are the top.
Yeah, Ethan?
Should fluorine have lone pairs?
Yes, I'm sorry, I just didn't draw them on that. Yes, fluorine should have 3 lone pairs around.
So even if one of the outer atoms has lone pairs, that doesn't affect it as a whole?
Yeah, that's right. Lone pairs that we're talking about in terms of polarity, the lone pairs that matter are the ones on the central atom. Yep, good question. Okay, we're going to look now at something called intermolecular forces. This is our last little topic with chapter 6. There's a difference between inter and intra. Anyone know the difference between inter and intra?
Inter is like when you inside.
Inter
is on the outside.
Backwards.
Inside.
No, other way around. Inter means between two things. Intra means within. So intermolecular forces means these are forces between two different molecules. Between two molecules. So not bonds, right? The intramolecular forces are called bonds. Inter means this is between two different molecules. So between a water molecule and another water molecule, that's what's holding it together. It's something called intermolecular forces. And you'll see me abbreviate intermolecular forces just with an IM, right? Intermolecular. So I'm just gonna talk through this next section. You don't have to put this part in your notes if you don't want to. So when you are melting something, it's going from what state to what state?
Solid to liquid.
Solid to liquid. Good. And so from a solid to a liquid, what do we have to do to get it to go from a solid to a liquid?
Turn the heat.
We got to turn the heat up, which means if we add heat, that means we're adding energy in the form of heat. Okay? So when we're in the solid state, our particles are held really tightly together. As we add heat, we add energy, which causes those molecules to start moving, which causes the bonds between them to break, which allows them to now move freely in liquid form. Right? The same would go from liquid to gas. As we start to add more heat, we add more energy, the bonds start moving more and more, and they separate, and now they're gas particles, right? So that's what happens when bonds break. It's not just miraculously things just start to fall apart, right? The energy between, or in the form of heat, starts to break those intermolecular forces, okay? So energy is what's used to break those intermolecular forces that hold molecules together. So if we have a higher boiling point and a melting point, that means we have really, really strong intermolecular forces. So what do you think in terms of groups on the periodic table or regions on the periodic table have the highest intermolecular forces? Like the metals or the non-metals or the, what do you think? Metals have the highest boiling points, right? Which means they probably have the strongest intermolecular forces. I want you to open your book real quick to page 204. If you don't have your text, listen. If you don't have your text, some of these. These are boiling points. So for oxygen gas, what's the boiling point for oxygen gas? Negative 183 degrees Celsius. Negative 183 degrees Celsius. Is that hot or cold?
That's pretty cold.
Oh, cold.
Negative 183 degrees Celsius. That's cold.
That's so cold.
So
That's a little nippy.
it's this is the point at which oxygen goes from a liquid to a gas. So this is its boiling point. So for oxygen to be in liquid form, it has to be colder than negative 183 degrees Celsius. Highest boiling point is for W, what element is W? Do you remember? Tungsten, good. And its boiling point's 5,660 degrees Celsius. So it doesn't become gas until 5,660 degrees Celsius. So really strong intermolecular forces. Okay? As a whole, metals have stronger intermolecular forces than ionics, which have stronger intermolecular forces than polar covalents than nonpolar covalents. Okay. So we're going to talk about, there's two types of intermolecular forces, and we're just going to talk about them just briefly. The first intermolecular force is called hydrogen bonding. And this happens when we have an attraction between the hydrogen in one molecule and some other molecule in another, some other atom in another molecule. Okay? Hydrogen bonding. This is the strongest intermolecular force. So you might want to put that there and star it. This is the strongest. Okay, the strongest intermolecular force. It happens between a hydrogen in one and another atom of another molecule. So you got to have hydrogen there to have hydrogen bonds. Hydrogen bonds are what causes water's surface tension to be so high. Okay, you know how when water bubbles up, it kind of forms kind of that, either the meniscus or it forms kind of a bubble on the top. That has to do with these hydrogen bonds. Okay, hydrogen bonding has a tricky name because it's not truly a bond. We don't share electrons or trade them. But it's a really strong attraction between two atoms. Okay, if you see a dotted line in a drawing like the one here, that's what a hydrogen bond is, because it's kind of showing it's kind of a bond, but not really a bond, right? Even though someone named it hydrogen bonding. Okay, so I'm going to walk through what this little picture means here in the bottom. And just follow along best you can. You don't have to draw this or really, if you don't totally wrap your head around what I'm saying, that's okay, but I'm going to show you what it means to have a hydrogen bond. So, within a water molecule, which of these is more electronegative? Hydrogen or oxygen? Right, we said that in our water molecule, our dipole moment looks something like this, right? Here's our lone pairs, blah, blah, blah. So within this bond, hydrogen takes on what we called that partial positive, and oxygen takes on that partial negative. Do you remember when we talked about partial positives and partial negatives just a little bit ago? Okay, it's just electronegative enough that those electrons are shading toward oxygen, which forms what we call that little partial negative. Okay? Yeah?
How do you tell which one's partial negative and which one's
The little, right, this one right here. Or you mean like...
how do you...
Okay, the more electronegative one is partial negative because it's taking the electrons closer to it.
Oh.
Yep, good question. So the same thing would happen in the other water molecule. This oxygen would take on a partial negative. a partial positive. So the hydrogen bond forms between this attraction of the partial positive on this hydrogen and the partial negative on this oxygen. That's where that hydrogen bond is formed. Okay? So these are really strong. They're not strong enough to really, completely hold them together because water still has to break at some point, right? When you pour things, it doesn't ever, it's not non-stop, right? It's got to break somewhere. And adding enough heat will break those bonds as well. But for the most part, hydrogen bonds are pretty strong. That's what causes high boiling points and high surface tension in hydrogen-containing molecules. Okay, so that's how a hydrogen bond works. The second type of intermolecular force is much more simple, and it's called a London dispersion force. These are the weakest intermolecular force. Okay, these are the weakest type of intermolecular force. So hydrogen bonds are only found in molecules that have hydrogen, but these London dispersion forces are found in all molecules. They're very weak, and they come from electrons and the creation of instantaneous dipoles, which I'll talk about here in a moment.